All right, so again, Section 7.3 is very similar to Section 7.2. Only difference is we are dealing with quantitative data here as opposed to categorical. So we're going to be dealing with sample means is what we're going to be working with instead of proportions. When we record quantitative variables, we are interested in other statistics such as mean, median, and standard deviation. Sample means are among the most common statistic. You can do standard deviations, but most of the stuff we do with AP is means and proportions. We don't do a lot of stuff with medians as we do these sampling distributions or standard deviations with as the main focal part of the sampling distributions. So they said consider the mean household earnings for a sample size of 100 people. So that's what this first one does. We're doing sample sizes of 100. What can we tell about the picture there on the left-hand side? How would you describe the shape on the left? Yeah, skewed right. So we would say it's skewed right. Where do we think roughly mean is just looking at that rough look there? What does that look like it's probably close to? About 75 to 80, somewhere in there? I mean, it's hard to tell, but it looks like it's probably right around in that ballpark. It's definitely not halfway at 50. It's not real close at 90, so it's somewhere around that ballpark. And then what is our range? Well, we go from basically 0 to, looks like that's smack dab there. So our range looks like about 250 is what our, basically it's 250,000 because that's our units, 250,000. So the mean looks like it's around 75 to 80,000. I'll put the K's on there. And then our range is somewhere about 250,000. Over here on the right-hand side, and again, that's the population distribution. Now from there, they decided to do a bunch of random samples of size 100 from that data, and that created our sampling distribution. So each one of those data points in this graph are all just different 100 random samples of the population from the left. And notice what happens to the shape. The shape gets what? Definitely more normal, more symmetrical. Okay? It definitely got more normal. Okay? Because as we look at it, got more normal compared to this one that we saw. It said was right skewed. Okay? What about our mean of X bar? Mean's going to be probably smack dab in the center there, which looks like it's about this, maybe the same. Maybe it's a little bit closer to the 80 mark. All right, maybe closer to the 80 mark. Again, because it's not as spread out, so it's more tightly in somewhere on that center there. And then what would we say that the range is? It looks like we're going from 50 to 100,000. So it looks like it's got a range of 50,000. And again, what do we notice about the spread as we do the sample size for the sampling distribution? The spread decreases. All right, so some little fundamental notes here. When we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean and population mean mu, and is less spread out than the population distribution. Again, here are some of our facts. The mean and standard deviation of the sampling distribution is X bar. So if mu is the dead center, then our sampling distribution, mu X bar, is the same thing. It's the same amount. Again, we want to, that's how we label, mu X bar is equal to mu. The standard deviation. The standard deviation of our sampling distribution is equal to that fraction. I have it primed up over here. Standard deviation of X bar. It is the population deviation divided by the square root of the sample size. So not as a crazy fraction like what we saw on the population stuff. Okay, it's just population standard deviation divided by the square root of the sample size. Again, we can do that as long as we meet the 10% condition still. These facts are about the mean and standard deviation of X bar, and they are true no matter the shape of the population distribution. So it doesn't matter if their population distribution was skewed. Okay? When we do the sampling distribution, we can go through and calculate these two things. So, real quickly, suppose that the number of movies viewed by a student in the last year by a high school student has an average of 19.3 with a standard deviation of 15.8. So in this case, mu is equal to 19.3, standard deviation of 15.8. Suppose we take a simple random sample of 100 high school students and calculate the mean and number of movies viewed by these the members of the sample. So they ask us to find what is mu sub x bar. Well, we know that's equal to mu, which is equal to 19.3. And then we're going to make sure we get in the habit of writing down units. That way they don't dock us on little petty stuff. All right, what is the standard deviation of X bar? Check to see if the 10% condition is met. Okay, so with that in mind, n was equal to 100. 10 times 100 is 1,000. Reasonable to assume more than 1,000 high school students. All right. Again, we can't just say, yes, it's met. We got to show it, got to give a little justification. Reasonable assume there's more than 1,000 high school students. We have more than 1,000 high school students at our school. Okay? So, now, what's the standard deviation? Standard deviation of X bar is equal to the population deviation divided by the square root of n. So, 15.8 divided by the square root of 100, which is 15.8 divided by 10, which is 1.58 movies. Sampling distributions of a sample mean from a normal population. Suppose that a population is normally distributed with the mean of mu, standard deviation of sigma. Then the sampling distribution of X bar has the normal distribution with a mean of whatever mu is and a standard deviation of sigma divided by the square root of n. Sorry, I left off the square root as I pre-filled in your notes. Square root of n. Sorry, you want to put that on there. I accidentally left that off. As long as the 10% condition is met. And remember, this is true no matter what the sample size is. If they told us that the population is normal, sample size doesn't matter. Okay, they can say the sample is 10. If they gave us that it was normally distributed, the population, we can kick off the piece of, because usually when we think of something that small as size 10, it may be skewed. So here's an example. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with a mean of 266 and a standard deviation of 16. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. Now, we know we want to do a normal CDF because they said that this was approximately normal. We're trying to find that the probability that X is greater than 270. That's what we're trying to find. So my lower bound is 270. My upper bound Heaven forbid that a pregnancy lasts more than 100,000 days, but maybe we scale this one back to say more of like the 1,000 days for the context. You can put down a big number, but at least for women, we don't want them that pregnant that long. I'm trying to think. There are some animals that have like long pregnancy terms. So what is our mean? Our mean is 266. Our standard deviation. Did we take a sample? Right now, at this moment, did they say there was a sample of size something? No. So that means our standard deviation is 16. There is no sample yet. There is no sample, so we just use the population standard deviation here. We don't do that formula. We don't do the formula until they tell us that we did, like on the next example, a simple random sample of 6. So in this case, this is just normal stuff. We go through, plug that into a normal CDF, and we should get something that is about this, approximately 0.4013, just to try to save us some time. I went ahead and rounded to the 4th decimal accordingly. So the probability that a pregnancy lasts more than 270 days is 40%. Okay? 270 days, roughly 9 months, right? Okay? Even though a pregnancy is 40 weeks, is 10 months. So there's a 40% chance that we last more than 9 months. Suppose we choose a simple random sample of 6 pregnant women. Let X be the mean pregnancy length for the sample. What is the mean of sampling distribution? So mu sub X bar would be equal to mu, which is 266. What is the standard deviation? We got to check the 10% condition. So if n is equal to 6, then 6 times 10 is equal to 60. Reasonable to assume more than 60 pregnant women. So now I can do the standard deviation. So standard deviation of X bar is equal to the population deviation divided by the square root of the sample size. So population was 16 was its standard deviation, divided by square root of 6. And then that gives us the following decimal, 6.53197267. Now, why did I write those all down? That way we have it for the normal CDF feature. But again, I'm going to use the calculator and type a formula to make it go a little bit easier. Part 4, find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. So what's the probability that X is greater than 270 days for this sample? That X bar is greater than that. So normal CDF. My lower bound is 270. Again, our upper bound, we can let it be 1,000 still. My mean is 266. The only difference is my standard deviation. My standard deviation is 16 divided by the square root of n. So that's what I'm going to do on the calculator. Now, the alpha button doesn't work on the normal CDF feature. So when I go second vars, normal CDF, the nice thing, I didn't do this one, so I didn't keep it. 270, 1,000, and then 266. The alpha y equals to get a fraction doesn't work in this mode. So so we can just go ahead and type in 16 divided by second square root, type in our 6. Okay, so we have to type it in that way. That's why I didn't type in that fraction with the 2 fractions on the previous one, the difference, because it was just going to be really crazy to try to type it in with all the parentheses. Okay, so then I'm going to hit paste, and we find out that our probability is approximately 0.2701. So there's a 27.01% chance that the mean pregnancy length for the women in this sample will exceed 270 days. All right. Next problem, it says the height of women follows a normal distribution. Sweet. With a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that the randomly selected young woman is taller than 66.5 inches. You want me to give you a second to do this one by yourself? Yes, and all right, we'll give you a chance to do this one by yourself. You focus on your iPads, you do it that way. I'm going to silently solve it without you knowing it. All right, so as I went through, I did what's the probability that X is greater than 66.5 inches, X being randomly selected young woman. And I guess we use the X bar since they use X bar. We would say equals a normal CDF because they did tell us it was approximately normal, so we didn't have to do any of the checking stuff. Lower bound, upper bound, mean, I kept the same standard deviation because this was not a sample. And I came up with 21.1 or 0.2119. So there's a 21.9% chance that a randomly select young woman is going to be taller than 66.5 inches, is what that means. Go! Why is the mean 266? Because Mr. Stevens wasn't paying attention. It should be 64.5. Mr. Stevens was not paying attention. He just started filling in stuff and remembered the 266 from the last problem. So thanks for catching that one. The math does work out right. If I looked at my notes, I would have saw I had 64.5 there. All right. Find the probability that the mean height for a simple random sample of 10 exceeds that. Again, we would need to do the 10% condition. So is 10 times 10 is 100. Reasonable to assume more than 100 young women. Okay, reasonable to assume that. And then now, I could, with that in mind, I can do my standard deviation of X bar, which would be 2.5 divided by the square root of 10. So normal CDF, lower bound is 66.5, upper bound is something really tall, mean is still 64.5. My standard deviation is now that fraction. Again, if you want to make it a decimal, that's fine. Just make sure you use all the decimal places. Is what you got to make sure you do. So, normal CDF. I'm going to start typing in my stuff. 66.5, 1,000, 64.5, and then can I carefully edit that? No, let's just clear it. 2.5 divided by second square root 10. That would have been easier. And after a couple enters, we find out that 0.0057. So there's not even a 1%. There is a 0.57% chance that if we randomly select 10 young women, that the mean height will be greater than 66.5 inches. So that's pretty rare. It's going to be pretty rare for us to get a simple random sample of 10 young women and their mean height will be greater than that amount. Okay? How many of you young ladies in here are taller than 5'6.5"? All right, just one. Okay, so when you think about it, it would be very rare. Of these 8 young ladies in this room, 7 of you are smaller than 5'6.5", and so it would be surprising to get if it did happen, because it's going to be very rare for that to happen. Okay, all right, let's keep on going. The central limit theorem. The central limit theorem basically draws, if we draw a simple random sample of size n from any population with a mean of mu and a finite standard deviation, the central limit theorem says when the sample size is large, and we're going to be using large as being n is greater than or equal to 30, the sampling distribution of the sample means is approximately normal. Now, note, how large a sample size is needed for sampling distribution is close to normal depends on the shape of the population. Many observations are required if population distribution is far from normal. We use n is greater than or equal to 30 to be safe. This is called the normal condition. Remember, we had a normal condition for proportions. In the previous lesson, in order for it to be normal, n times p had to be greater than or equal to 10, and n times 1 minus p had to be greater than or equal to 10. When we're dealing with means, n has got to be greater than or equal to 30 for it to be normal. Okay, so you may want to add that. I didn't add that in your notes. I leave some stuff out so we can write stuff to keep you guys awake. Okay? Now, I just realized I blew past the graphs in the middle. My bad. I'll give you a chance to copy that down. So here's going to be the challenge when we start doing the 4-step process with means and proportions. When you go to verify normal and we're dealing with mean or mu, you need to make sure you're using 30 as your number. When we're dealing with proportions, it's 10. That's probably one of the biggest, and then we get to use that for the rest of the semester. As we deal with proportions and means, no matter what topic I talk about, proportions is always 10, means is always 30. It only changes when we get to chi-square testing, which is like the last unit, okay? So let's go back up here. I didn't realize I just blew through that. I saw the time and I blew through it. So at this very first picture here, sample size n is equal to, there's our population, sorry. Here's our population. Okay, so this is the population. What can we say? It's got a big spread. It's definitely multimodal. It's got 3 distinct peaks. It's got a peak here. It's got a peak there. Got a peak there. Okay, that's one thing we can tell about the population. Now, in this next picture, they went through and they took a random sample size 2 from the population and created the following distribution, sampling distribution, with sample size of 2. All right, notice the spread got smaller. We still have a lot of distinct peaks here, but the spread did get kind of smaller. Next example was size 5. They went to sample size 5. Spread got smaller again. What also do we notice about now my picture? Is it starting to become approximately normal? All right, it's looking like it. It's getting a nice little shape here. May still have a little bit of a tail on the right side here to be a little skewed. Now the next one is sample size n is equal to 10. Hey, we're looking a lot better here. We're looking more approximately normal is what we're looking at. And the last one, they said we're doing a sample size of 25 from the population, and we do multiple samples. Now we notice what's happening. We're definitely getting closer to that approximately normal curve, okay? So some things to write down over here on the right-hand side. They asked us to describe the sampling distribution as n increases. What do we notice? As the sample size increases, the distribution or the distributions become more symmetrical and almost normal. Most population distributions are not normal. What is the shape of the standard shape? What is the shape of the sampling distribution of sample means when the population distribution isn't normal? Well, it's going to have some skewness. It's going to have some skewness, and that's okay. Okay, but as we increase the sample size from n is equal to 2 to n to 5 to 10 to 20 to 30, 40, we get more normal. It is remarkable that fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like the population and more like a normal curve. When the sample is large enough, and again, closer we get to 30, the better. The distribution of sample means is very close to normal. No matter what the shape of the population distribution has, as long as the population has a finite standard deviation, which means that, hey, it's a finite number, not an infinite number. I don't really deal with a lot of infinite stuff. So real quickly, in the last couple minutes here, we'll get to this next part here, this one example here. This other part just walks you through how to do, and there's a problem there, and I posted the answer there because I knew we weren't going to get to it. Just shows you how do we do the difference between means. We did an example with the proportions. We have to be able to do it with means. Again, I put the problem there and the worked out solution next to it. That way you have it. So last examples here. Suppose that the number of texts sent during a typical day by a random selected high school student follows a right skew distribution with a mean of 15. So mu is equal to 15. Standard deviation of 35. Assuming that the students at your school are typical texters, how likely is it that a random sample of, so n is equal to 50, will have sent more than a total of 1,000 texts in the last 24 hours? So our goal in the very last part, our goal is to figure out the probability that x is greater than 1,000. That's our goal. So do we meet normal? Our sample size is 50. That's greater than or equal to 30. Normal condition met. What is the mean? The mean is equal to 15. Standard deviation would be the old standard deviation divided by the square root of n. So that would be 35 divided by the square root of 50. And then we get 4.949747468. Woo! Now here's where we got to be careful. I was trying to speed up to get this part in here. They're telling us that 50 students would have sent a total of 1,000 messages. That's 50 for those. We need to figure out how many messages for one student. So what is 1,000 divided by 50? What is 1,000 divided by 50? It's 20. Okay. So we need that for the lower bound. Because if we just flat put in 1,000, put in a big number, and then the other stuff is going to give us 0. Okay? And so we need to fit, again, this is all 50 cent a total. So we got to figure out, well, how much did each one roughly spend? 20. Or they sent. So 20 is our lower bound. Our upper bound is something really big. Bigger than 1,000, because 1,000 is what we have there. Our mean is 15. Standard deviation is 35 divided by the square root of 50. And that works out to be 0.1562. Again, we have to be careful on, in this case, where they said the mean or the total of the 50 was 1,000 tech cents. So we had to break it down to an individual amount roughly. We don't always have to do that. I'm going to hit stop here.